Hey everyone, today's topic is virtual memory and it is one of the most important topic in memory management in the operating systems. So there will be many topics in this video. You can check those out in the description below, okay? We will be covering many topics related to virtual memory, paging, segmentation and many more, okay? So you can check them out and so this is a very important topic in the whole series. Okay, so let's begin. So with paging and segmentation, we have seen that the logical address in the program are translated to the physical address and they can be different each time when the program is removed and swapped back in the main memory. Okay, and we have also seen that the process or the program is broken down into segments or pages which need not to be in continuous order. Okay, they can be stored in non-continuous order in the main memory. Okay, so since and we have seen that we don't need all pieces of a process to be in the main memory at a time. Okay, only some part of the process is working at a time. So only a few pieces of that process are needed in the main memory at one instance. So the pieces of the process that are in main memory at a time are known as resident set. Okay, are known as the resident set of that process. So it require so when the process is executing and there is some portion which is required and it is not in the main memory, so the memory can't be accessed and there is an access fault. So when this happens, the OS issues an IO interrupt. Okay, so issues an IO operation and it puts the current executing process in the blocking state so that blocking state and it moves on to some other process and the IO issued interrupt fetches the required memory portion into the main memory, which can be dealt later as per the scheme employed by the OS. So when the portion gets loaded back, it generates an interrupt to notify the system that the required memory is here. So the OS can put it back into a ready state and can start with it again later on. Okay. So by using this strategy, we can make out two things that only some part of the processes are needed to be in the main memory. Okay. So what does that mean? That only if some part of the process is main memory, we can say that there are many processes whose some part is in the memory. So we can say at one time there are many processes in the memory. Okay, many different processes. Many of them can be in ready state, which will be good at it will maximum utilization of the CPU power will be done. Okay, so by keeping only some part of the process in the memory, we can keep many processes so that we can find a ready process at any time for the process to execute. And the another good thing with this is that since we are keeping only a part of the process in the main memory, the process can be even larger than the main memory. Okay, now they don't have a restriction to their size. Okay, as only some part is in the main memory, they can be very large as compared to the main memory. So main memory is called the real memory because this is the place where all processes get executed. Okay, the memory larger, but what the programmer perceives as the process or the program or anything or can be larger than the main memory. So The programmer doesn't take into consideration what's the size of the main memory. It creates its own memory references, and the thing that the programmer considers is known as a virtual memory. Okay, so it relieves the user from the main memory constraints. Okay, he can be as flexible as he wants to with memory references. Okay, they need not to be real actual places. Okay, so the memory perceived by the programmer is virtual memory. So th- there is a big discussion that went on a few years before, that is, it is really practical to imagine virtual memory. It is really practical to apply such a technique. Okay, there was a long debate, and it was later found out that it actually helps. Okay, as we use only a short portion of a program at one particular time, so it will be a real waste to load everything, that is each portion of the process at one time, keeping into main memory will be such a waste. Okay, as we are using just a simple few pieces only, so there is no need to load the whole program in the main memory. Okay, so now this is where OS comes in. He needs to be smart to do the swapping of which pages he requires, and the swapping should be smart. Okay, that's the only way the efficient working can be guaranteed. Okay, say it swaps out a process, that is, it swaps out a page which was needed just after that, so another page fault and another reading operation will be done. So this is bad. Okay, he needs to be smart. So if this condition goes on where he swaps out processes that are needed again later on, and so a lot of time is wasted in this continuous swapping process, and it leads to a condition which is known as thrashing. Okay, thrashing is this condition in which the system spends more time in swapping, which should have been given to the executing of instructions. Okay, a lot of time is wasted in the swapping process. So the technique should be smart. Okay, which pages to swap out. So to help us decide which pages to swap out, there is a principle of locality. Okay, this is the principle that makes the virtual memory a reality, make it practical. Okay, so the principle of locality states that the program and data references are tend to be in cluster. So it's easier for the system to make guess of which portions to swap. That is, they are localized in a place, the data references and all. So system can make a pretty good guess of which pages to swap. As in data there are references, so those references will be nearby that data. Okay, they won't be in far away memory. So the principle of locality helps the OS decide. Okay. So to make the use of virtual memory, what we need? First, we need an hardware that supports our previous claims of the schemes known as paging and segmentation. And the second and more important thing is the software that can do effective swapping of these pages. Okay. We discussed paging before, how paging is done, that the system is that the processes are divided into fixed size blocks known as pages, and the memory is also divided like those fixed size blocks known as frames. Okay, so and all this information of which page is assigned to which frame is kept in the page table, and in the page table the p bit is, there is an additional p bit which can be kept to denote that the page is in the main memory or it's not. It's in the secondary memory right now, so it needs to be loaded. So yeah, page table can store the information in the p bit, okay, as a single bit to denote. If 1 means it is the main memory, if 0 it is in the secondary memory, okay, we can say that is the p bit. And another bit can be used known as m bit to denote that the page is modified or not after being loaded, okay. So if it was modified, it needs to be written back to the secondary memory before it is removed from the main memory, okay. So based on these bits, better swapping decisions can be made. Okay, we'll see that. See, this is the virtual address, huh? And this contains our page number and offset. Okay, so we discussed last time that virtual address consists of n and m. The n is the page bits and the m is the offset. Okay, with this n bits, we first n bits we get the page number. Okay, by adding this to the location of our page table, which is pointed by a register, we get the so by adding this page number, we get the location of the frame number. Okay, so offset is same, and now the real, actual, physical memory obtained is this. That is the frame number and the offset, which is the actual place in the main memory. So we can use the page number to get the frame number from the page table, and adding it with the offset gives us our desired physical address, okay, which is in the main memory. There are many variations to this page table scheme, and there can be hierarchical page table. That is, there can be two levels of pages. Okay, one page table points to another page table, so there are hierarchy between those. Okay, the another scheme is inverted page table, which uses a hash function. Okay, which maps a bit of page number to a m bit quantity. Because the problem with this is that previous one is that the size of the page table was proportional to the virtual letter space. Okay, as the virtual letter space was large, the page table was also large. So to get rid of it, we can use of a technique known as inverted page table, which hashes the page number and confine it to some given quantity, so the page table doesn't expand much in size. So as some of you may be knowing that in hashing there is chains and there can be multiple mappings to one particular part. So it's a detailed topic we are not looking into, but just to show, there are two techniques we can which employ this page table, that is hierarchical and inverted. Okay, so the next one is translation Lookaside buffer. As we know that for every virtual memory reference, there is two memory fetch. One is to get the page table and other to get the required data. ठीक है? Other to get the required data. So a lot of time is wasted in this, and we try to improve it. So to overcome this problem, most OS systems make use of a cache known as a TLB, translation Lookaside buffers. What it does, it just keeps the recent used page table entries. So if they are referred again, they do not need to go to the page table again, and they can be directly get from this buffer. Okay. So what happens with the translation look aside buffer is, for the OS checks if this entry which he requires is in the TLB. Okay, so before going to the page table and anything else, before checking any memory, it The first thing OS does is it goes to the TLB. Okay, if the required entry is there, yes, it's great. It's known as a TLB hit. Otherwise, bad luck, no, it's a miss. So if now the processor follows the previous approach, as we have seen before the TLB, it conserves the required page table, and if the present bit is there, means the page table is in the memory, that entry, that process is in the memory. Otherwise, it has to be fetched from the secondary memory. So it's the same as before, just like, just the difference is the first thing it looks into is now the TLB. Okay. So yeah, if the page is not there, it generates a page fault, and the OS fetches it from the secondary memory and updates the page table, the present bit to 1 to say that yeah, now it is in the main memory and you can access it. Okay, so see the situation has changed with the TLB in picture now. So this is the page number and this is the offset. So for the page number is checked with the translation Lookaside buffer. So if it is found, it's a hit and we can directly get the frame number from this TLB. When added with the offset, it generates an address which is the actual desired address and which is in the main memory. Or what happens is it is a miss, the entry was not found in the TLB, so it goes to the page table, gets the frame number. Okay, and again with the offset added, we get our desired address. Or another thing can happen is that there was a fault and it was not in the main memory either, the page table. So what page was not in the main memory? So the what OS does, it goes to the secondary memory, fetches that process, the address, the memory, the location, and puts it into the main memory. It updates the page table to represent the present bit key. Yes, it's in the main memory. So that's how it works. Another thing to consider now is the page size. Okay, so what should be the page size? To reduce the problem of internal fragmentation, we can think that the page size should be small, so that there won't be little space left after the process is assigned. And small size would mean there are more pages per process, which leads to another problem, that is the page table will be larger. As there will be more pages, the size of the page table will increase. So you may counter that with that, like, you can say, why don't we make it large? Okay, why don't we increase the size? Well, if the page size increased, the fault rate also increased. Because see, when the page size was small, the memory references pages in those small pages were nearby, as the portion was small. So those nearby pages were also in the memory, and there were few page faults. But if we increase the page size, the data references and all the locations referenced in those big portions will be far away. And it's not necessary those far away portions will also be in the memory, as there are much fewer portions in the memory right now. So by growing the page size, the fault rate will also increase. Okay. And so this growing of the page size is what weakens our principle of locality, which was a most required component to support our virtual memory claim. Okay. So as you can see the graph with page fault rate and page size. So as the page size increases, the fault rate increases. Okay. And it becomes zero when our page size equals to our process. That is, our whole process is there in the main memory. So of course there won't be any page fault in that. Okay, so the general is it increases with the page size or number of page frames allocated. Okay, so it is like how many pages are allocated per frame. Okay, so the more the page frames are allocated for a process, the less will be page fault. Means if we allocate lots of frames to a process, so the whole process get loads up in the main memory, there won't be a page fault. And if like only two frames are allocated to the process, so what he needs to swap again and again to keep on processing, so there will be many page faults as very few frames are given to that process. So page size is really a concern, and the objective-oriented programming and the multi-threaded applications decrease the locality principles. As with modular programming and many threads running at the same time, they make abrupt dynamic references to the various parts of the process which are not in the locality. So what happens is if the locality decreases, the TLB hits decreases. Okay, because TLB was keeping track of the recent things, and if we are not in the locality and we are referring to various different parts of the processes, so there won't be a recent relationship between any of them, so the TLB won't be able to provide much of a help to our process. So TLB becomes a bottleneck in that condition, because every time we are going to the TLB first to get our page, and TLB is not able to provide a stat. So now this time is kind of a waste. So TLB becomes a bottleneck in that condition, and it does not serve any purpose if the locality decreases. The solution for that is we can use a larger TLB. Okay, but it is not as easy as it was with the memory, because TLB is a hardware and it affects many aspects of the OS. So increasing the TLB is not an easy task. Okay, so or we can think of increasing the page size. Okay, so that it refers to large areas. But we have seen in the previous two slides that if we increase the page size area, it's again going to reduce locality, as the references will be much further away than they were in with small size. So yeah, this can't be done either. So to get so the page size to help something to the so many investigators did some investigation of what to do with this condition, and they came up with multiple page size approach. Okay, there are several microprocessors nowadays which support this multiple page size, but still most of the most of the OS systems still supports only single page size, as the management of this multiple page size is really complex. Okay, it's a complex task to manage various page sizes, their allocation, and how they are managed. And there will be a lot of different hardware and OS policies required to do that. So most of the OS still go with single page size approach. Okay. So the next one is the segmentation. We have discussed segmentation before. Segmentation is how the user visualizes the program, and it is much easier to do the sharing and protection tasks in the segmentation. Okay, there can be like sharing and protection bits in the segments which denote that yeah, this can be shared, this is the protected segment and all that. Okay, so like the page table, there is a segment table which contains the segment number, which refers to the starting address of the segment, and also it contains an entry which denotes the length of the segment. and as well as there is a present bit or modify bit to denote whether it's is in the main memory, or modify bit to denote whether it has been changed since it was first loaded. Okay, so yeah, the same as before, the offset can be added to the base starting address which we obtained from the segment table to get our desired address. Okay, so this is how it's done. It is same like the page table almost. So the segment number is matched with the segment table, and we can get the length and the base address of the segment, which is then added with the offset. So we get an actual physical location which is in the main memory to get our desired physical address. Okay, so now these both approaches have their own advantages, as the paging eliminates external fragmentation with its fixed size, and it is easier to employ various algorithms in paging. As the size is fixed, it is much easier to employ various kinds of algorithms. And segmentation provides visibility to the programmer, and it is much easier to handle data structures in segment and to create modules and all the protection and sharing stuff. So yeah, everyone has its advantages, and to make the best of both, we combine them. Okay, so the combined paging and segmentations are like is the technique used mostly by every OS I can think of. Okay, so this is a good technique, as it takes advantages of both. So now it consists three parts. Like the logical address consists of three parts. First is the segment number, second is the page number, and the third is the offset. Okay, what the segment number does is it points to the page table. Okay, and so in the so we use the number, and we go to the segment table. Okay, the segment table consists the page table page number. Okay, not the page number actually, it's a reference to the page table, and also contain protection and sharing bits. Okay, whether the segment is shared or protected, and with that found we get the page table. Now we use the second part, that is this page number. Okay, you match it with the page table and we get the frame number. And now the frame number, when added with our offset, gives us the desired physical address. So now this is the whole scheme. Okay, this is the virtual address, consists of segment number, page number, and offset. This segment number is matched and found in the segment table. So when its entry is found, it points to the page table. Now the page number is used to find the page number from this page table, so which gives the frame number, and this frame number is then added with the offset to get the physical memory location which is in the main memory, and we get the desired location. So this is the combined approach of segmentation paging. So this is the best technique till now we have covered with paging and segmentation. So yeah, we will covering various fetch policies and how the pages are fetched and how they are removed in the future videos. So keep watching them. So yeah, this is this is the end of this video. So please hit the subscribe button and the like button also. And you have any problem, you can comment down below. Okay. So yeah, thanks for watching.